All right, everyone. Hello and welcome. Due to some technical difficulties, I'm having to re-record this after having already filled this in. For some reason, the video didn't save correctly. I'm just going to leave the writing that I had and instead kind of walk you through what I do. So that's my bad. I don't really know how the video kind of messed up, but here we are. So it occurs to me that on page 3, I should have, at the very bottom here for part C, this was where I was supposed to write the numerator, the fact that the numerators are equal. So just go ahead and write that here. And in fact, I even rewrote it just because instead of having to scroll up a lot, I just rewrote it here as well. And so what we need to do is, as you'll remember from Calc 2, we need to solve for A, B, and C. So there's a couple ways to do this. The Calc 2 way is to say, okay, well, I can expand this expression, I can expand this expression, and I can expand this expression. And then you would group everything together according to powers of the variable s, right? So you'd have some numbers or some expressions with a, b, and possibly c times an s squared. You'd have some stuff with a, b, and c times s, and then you'd have just the constant term left over. And then you would equate those coefficients. So whatever is in front of s squared would have to equal 0 because there is no s squared over here. Whatever is in front of s would have to equal 7. And then whatever is the constant term that's left over would have to equal -1. Okay? But when you have non-repeated linear factors showing up in any one of these expressions here, another way you can solve for these coefficients a, b, and c possibly is by picking an s value that would eliminate a lot of, or most of, the other terms. So notice if I set s equal to -1, boom, this whole term right here is gone, and so is this term right here. And so all I'm left with is b times, well, -4, because I'm plugging in s equals -1, and then times +1, because s is -1. And on the left-hand side, I get -7 minus 1, which is -8, right? And so that tells me very quickly and easily that b must be equal to 2. So it's kind of a sneaky workaround. You'll notice here, when s is equal to 3, well, these latter two terms are gone, right? And all you're left with is, well, 21 minus 1 is 20, a times 4 times 5, which says that a equals 1, right? And then similarly, if s is chosen to be -2, it knocks out the first and the second term, and all you're left with is the third term involving only s, and on the left-hand side you get -15 when s is -2. And so here you go, right? And so c has to be -3. And the way you choose these numbers, they're not chosen randomly. They're chosen to be, if we look back at our denominator here, where is it? Right here. Notice I chose the s values to be exactly one of the 3 possible roots, -1, 3, and -2. Okay. All right, so now that we have a, b, and c, we rewrite capital Y of s. This is the partial fraction decomposition, right? A is 1, b is 2, c is -3. And now that means that little y of t is just the inverse Laplace transform of capital Y of s. So it's the inverse Laplace transform of this expression right here. And now that we've decomposed it into fractions that we can find on our table, so look at the right column of one of the 2 tables that I gave you. I think they're both the same. You'll see here that a number divided by s minus a number or s plus a number, all of those are on there. And now you can split up and just do the inverse Laplace at plus and minus signs. And so you get 1 over s minus 3. The inverse Laplace of that is e to the 3t. 2 over s plus 1, the inverse Laplace of that is 2e to the minus t. And minus 3 over s plus 2, the inverse Laplace is minus 3e to the minus 2t. Okay. And I encourage you to check this against, like, finding a characteristic polynomial and then, finding the complementary solution, and then taking a guess what the particular solution has to look like and using the method of undetermined coefficients. We learned all of that in Unit 3. I encourage you to give that a shot and see that you get the same thing. Okay, And now for this process, I kind of break it down for you. The thing that you do first is, well, if you go back above, we found the Laplace transform of this whole differential equation. And then we solve the resulting algebraic equation for capital Y of S. We found the partial fraction decomposition if necessary. In this case it was. You'll notice that I think it was homework 4-1, unit 4-1 homework. You did not need to use a partial fraction decomposition to solve those differential equations. But moving forward, you might, more than likely. And then here, number 4 is just once you have that decomposition, just take the inverse Laplace of it. And we call that little y of t, right? Or just little y, you can suppress the variable. Okay, and now number 8 here, coming to the last part of this section before we quickly discuss the homework. If you ever encounter something like this, you'll notice that the denominator, while a quadratic and while it does factor, it does not factor over the real numbers. This factors as s plus 5i quantity times quantity s minus 5i. And unfortunately, that's not really going to be good enough for us. If we are going to factor, we want to be able to factor like above over the real numbers, right? And so we're actually going to leave it like this. And we call this from Calc 2, you might remember, this is called an irreducible quadratic, right? S squared plus 25 is an irreducible quadratic. And so we leave those as they are, but if you have some stuff in the numerator, split it up according to any plus or minus sign. So here, this is actually, if I want to find the inverse Laplace of this expression, it's the inverse Laplace of 3s over s squared plus 25 minus the inverse Laplace of 8 over s squared plus 25. And now this Laplace transform here, the first one is easy. You look at the chart, it should be near the bottom. You have cosine of bt, the Laplace of that is s over s squared plus b squared. Well, notice here's my s, and b looks to be 5, right? So I think this is just 3. Notice this factor of 3 can really just push out here if you like. This is just 3 times the cosine of 5t, right? However, here, this one looks a lot like the sine Laplace transform, and so its inverse should involve a sine. But in order for this to work, I technically need a 5 up here, right? Well, what I'm going to do, and what I do right here in this step, is cleverly multiply by 1. So notice, I can get my 5 up in the numerator if I then multiply by 1/5, right? And so technically the numerator is still 8, right? It's 8/5 times 5 is still 8, but I'm making it look a little bit different now because I need the 5 over s squared plus 25 in order to do the sine Laplace inverse. And so this 8/5 actually factors out now, and then you get sine of 5t. And so that trick, I don't know if it's a trick, but that strategy should help you for some of these later problems for number 1, and then possibly looking ahead into number 2 as well. But just a couple remarks. I think part A should be pretty straightforward. You just look straight at the table. Expand the numerator for this one first, and then maybe split up the fraction. That's a pretty straightforward example. This one, maybe take a factor out of each denominator so that it looks like something from the chart. Here, maybe that strategy I just showed you above could help you here for the Laplace inverse of this one here. Same here. For, I think, the last 4, you're going to need to use a partial fraction decomposition. And notice these last 2, number 1 parts h and I, have irreducible quadratics. So when it comes time to find the inverse Laplace of the irreducible quadratic part, see above, see number 8 above here, right? And then here we actually put it all together into the strategy, which is number 7 here. So this is the steps you're going to follow, but you'll need to do some work. All right, so that's the end of this section. In the next video, we get into Unit 4-4.